Hello, Math 120, and this is Professor Gonzalez, and I'd like to do some problems from Homework Section 8.4. Now, 8.4 comes from a section called Properties of Logarithms. So let's see, 8.3, we did some of these problems by using the definition and converting the logarithm to exponential and figuring it out there. And this still would work that way too. But there's properties that gets us there even that much faster. So let's take a look at some of these properties and go from there. And I think I'll try to tie in 8.3 a little bit using the definition showing you can do it both ways. But the properties certainly make things much quicker. So I'm going to scroll down here to take a look at some of these properties that I typed up here for you or did a screenshot. So anyhow, rules of logarithms, also known as properties of logarithms. Let me zoom in here. And the first one, rule number one, and you don't really have to call it rule number one, but you have the product of two logs can be rewritten as the sum. Now, notice the bases are the same. So we're looking at this one right here. Our first, whoops, come on. For some reason it wants to do something weird. Okay, our first rule right here, we're taking a look at that. And we're saying that when we have the log of log base b, so it could be any legal base. Let's go down here and see what's a legal base. Well, what a legal base would be is if your b is greater than 0 and also b cannot equal 1. And remember the m and n are arguments. And so let's see, let's do this down here. Whoops. So it says m, n, and k are real numbers, but I really should be a little more clear. M must be positive, so m is greater than 0, and n is also greater than 0. Remember that? We talked about the arguments needing to be greater than 0, so I'm going to put a little highlight on those two as well. So those are some real important pieces that we have to keep in mind. But rule number one. Now remember, we talked about logarithms and exponentials or inverses of each other. So they have some real similar characteristics you might be able to see here. Like for instance, notice how rule number one says log base b of m times n equals log base b of m plus log base b of n. Now notice the bases are the same. And what do we know in the exponential world, right? So this is a review. In the exponential world, what would go with the rule number one? Well, in the exponential world, if you had, what variables do I want to use? I'm just going to say x to the n, x to the n times x to the m. What do you do when you're multiplying two exponents with the same base? You do what? You add the exponents. And so look at the reverse of that is happening with the logs here. Okay, and then also rule number two, it says if you have log base b of m divided by n, rule number two is often called the quotient rule for logs. Rule number one is often called the product rule for logs. But you've got this quotient m divided by n can be rewritten as log base b of m minus log base b of n. Now sometimes you want to, most often we'd like to actually go in this direction and write it as a single log. Sometimes you want to go in this direction and break them down into individual pieces. So the rule can be applied in either direction with using the equality symbol. And in the exponential world, what would rule number two look like? Well, if we had x to the m divided by x to the n, what do you do with exponents with the same base? When you're dividing them, you simply subtract them, m minus n. So you can see there's a similar feel here with the quotient rule for logs. Once again, they're inverses of each other, and so they undo each other, and they have a real close relationship. Like what? Like, what are some other inverse operations? Well, if you were trying to solve this problem, right, a cube, and it had an equation attached to it, how would you undo it? Well, you would just cube root it, because the cube root and man, those don't even look like threes, and x cube are inverses of each other, so it would just undo each other and just become x. Okay, Often we think of x squared as it, but it's an inverse that has some restrictions on it. In fact, you'll remember, what are the restrictions? Well, what happens when you square root x squared, out comes the x, but you have to say absolute value. And that's because x squared, the function f of x equals x squared, is not a one-to-one function, so it kind of has problems. We have difficulties with this. Anyways, let's continue. And also, when you go to trigonometry, you'll find that you have sine and inverse sine, cosine, inverse cosine, stuff like that. And also, we have these guys. Let's see. Are we at the point where we're going to inverses yet? No, we're not. Our next rule, number 3, basically says that what you can do is you can take log base b of m to the k power, I'm going to write k in green, and you can rewrite that as a product of k times log base b of m. Those two statements or expressions are equal to each other. So that can be very effective in moving and simplifying this so we can possibly solve for something or whatever the job, whatever we're trying to do. Okay, rule number 4. Rule number 4, we actually did this problem, I believe, in 8.3, but we didn't have the rule, so we just had to use the definition of logs to do it. But rule number 4 basically says if you have log of any legal base, once again, bases be greater than 0, base cannot equal 1. But if you have log, on rule number 4, by the way, if you have log of any base of 1, this will always equal 0. So that's nice to know because sometimes if you see log base 13 of 1, look, that sounds like not a great number, but actually that is just going to be equal to 0. Okay, and I don't like how that looks, but let me try another one. So how do we know, how can we verify all of these things really? Well, let's go ahead and take that. This rule number 4 is basically saying log base, let's say 5, of 1 is going to equal 0 because log of any base of 1 is always going to equal 0. Well, if we apply the definition of logs and rewrite this as an exponential, how do we do that again? Well, I can't remember what colors I used. The base of 5 in the log becomes the base of 5 in the exponent. And so that means 5 to the 0 power equals, yeah, I do remember I used the argument was red, equals 1. And wait, 5 to the 0 power is 1. Yeah, any number other than 0 raised to the 0 power is going to equal 1. And that's why log of any base of 1 is always 0. You can see it clearly when you change it from the logarithmic form to the exponential form. So that's kind of nice to see. Okay, rule number 5 says log base b of b equals 1. What's going on there? Log base b, well, let's check it out again by looking at the definition. So rule number 5 says log base b, so let's put some numbers to it. Log base, let's say 7 of 7 equals 1. Well, if we go ahead, now this is, of course, is in its logarithmic form, and if I change it to its exponential form, how do we do that? Once again, I always start with the base because the base of the log is still the base of the exponent. So this is 7 raised to the first power. That will equal the argument 7. And yeah, any number raised to the first power is going to be that same number. So that's why rule number 5, that's how rule number 5 works. Log of any base of b, any base b of b equals 1, always. Okay, rule number 6. Now, rule number 6 is working on this inverse idea, like what I showed, that x cubed, if you cube root an x cube, right, it sort of peels away everything and you end up with what you started with, x. Okay, and that's kind of what's going on here. Okay, that's what's going on here. And let's do this. So number 6, it says log base b of base b. Well, log base b and base b are inverses of each other, and just like x, the cube root of x undid x cubed, so does log base b and exponential base b. And what am I left with? I'm left with just this k. Oops. Every once in a while, it just wants to freak out on me. Come on. I'm just left with this k value, which is the answer. That is going to be really handy to use. Okay. What would that look like? That would look like something like this. Log base, let's say 5 of 5 to the 6. Guess what that equals? You're going to quickly realize log base 5 and base 5 cancel each other out, and you're left with 6. And kind of the reverse of this is base b of log base b. This is rule number 7. Base b of log base b also will undo their inverses, and they sort of undo each other and cancel each other out, and you're still left with whatever's in there, whatever's in that argument, which is k. All right, and the only other rule I could think of that they didn't tell us is, and I don't know if I did this last, I'm going to do it again if I didn't, the change of, that looks like an A, the change of base formula, theorem. No. Change of base property, I can't remember. Change of base, I don't think it's a property. Change of base property. Okay, so the change of base formula basically goes like this. It says if you have a log. Now, by the way, if you had, let's go over here for 1 second. Remember on the calculator, what logs do we have on our calculator? If you have a scientific calculator, I mean, it could be used $8, $12 calculator. If it's scientific, on the calculator, it has a button that says log, right? And that is the common log. So that is log base 10. So we have log base 10 on our calculator. We also have the ln button, which is actually a log, a special log, log base e. So we have 2 log buttons on our calculator. So if you ever had to, oh wow, where'd my e go? Change. I didn't even see that. Change of base property. So if you had log base 10 or log base e, you could just use your calculator to approximate that. But what if you had some other base? So what if you had log base, and this, what if you had log base 5 of 6? Well, I don't have a log base 5 on my calculator, so I wouldn't be able to approximate it. But with the base change theorem or property, you would. You get to change it to any base you want. So what bases would you change it to? Well, I'm thinking of 2, one or the other, because I actually have those buttons on my calculator. So I'm going to either change it to a common log or a natural log. They both will give the same exact answer. So if I wanted to get an approximation, I would put in the calculator, let's go with the natural log of 6 divided by the natural log of 5. And that'll give me the same exact answer as if I decided to use my common log button, which would be log base 10 of 6 over log base 10 of 5. And they both will give me the same exact answer. Okay, so this allows us to approximate any base, because we're allowed to change it to whatever base we want, and we're always going to change it to the base of the functions we have on our calculator so we could actually put it in there. Okay? All right, I think it's time to do some problems. That was a long intro. Okay, well, let's see here. Use the properties of logarithms to find the exact value of the expression. Do not use a calculator. Okay? Well, the first thing we can see here is I'm seeing an inverse thing happening. Log base 2 and its inverse of base exponential base 2. This is just going to leave us with a 5. And let's see this one. We have the natural log. And remember, you might want to actually write this as, now you don't have to do this, but if you're kind of new at this, you might want to actually write this just to remind yourself of all the little pieces. The natural log is the same as log what? Base e. And then this says e to the negative 13. Oh, wait a minute. Now it really pops out that, okay, log base e and base e are inverses, and it's just going to leave me with a negative 13. Okay. Now this one, we've got a base 4, exponential base 4, raised to the log base 4. So once again, we have this inverse idea happening, and the answer is just going to be 3. So wow, these are nice and quick, aren't they? Same thing here, evaluate this. And if we want to, just to remind ourselves that this is e raised to, ln is log base e of 12. So the same thing's happening. We've got a base e and a log base e, which are inverses and undo each other, leaving us with a 12. So we're just, remember what we're doing here is we are using the newfound properties I think we're enjoying quite a bit. We just use these two properties right here, the inverse idea. Okay, so we keep this rolling. Now, what property is this? It says log base 6 of 1. Log base 6 of 1, log base b of 1 is always going to give us 0. So we know that this equals 0. Now, in a pinch, right, that's just for speed, but in a pinch, like in 8.3, we would have had to do it a different way. Log base 6, if you didn't have the property, log base 6 of 1, and we don't know what it equals, so we'll say, well, let's just make it equal to y. Okay, and then you just change it using the definition to an exponent. What's the base? 6 raised to the what? Y equals what? 1. And you would ask the question, well, 6 to the what power equals 1? Or you might actually go, let's see, 6 to the y equals, and 1 is 6 to the 0, so therefore y equals 0. But instead of having to go through all that trouble, we just use a property now because we know it's always true. Next one, write the expression as a sum or difference of logarithms. Express exponents as factors. Express exponents as factors, okay? So first of all, I'm going to see that this is a product. So I know I can rewrite this. I know I can rewrite this as log base 5 of a to the 4th plus log base 5 of b. Okay, now it says express all exponents as factors, and so we're going to use this rule right here. Whoops. We're going to use that rule right there, which says if we have an exponent, it can be written in front as a factor or product. Okay, so we're going to go ahead and use that at this step right here. This exponent can be written as a product right in front. So now I've got 4 times log base 5 of a plus log base 5 of b. And there we go. Written it as a sum of 2 different logs. Write the expression as a sum or difference of logarithms. Express your powers as fractions. Express powers as factors, rather. Okay, so once again, this is multiplication, so it's a product. Log base 2 of 4 plus log base 2 of x. Now, log base, this little guy right here, we actually can do a little more work with that. Log, let me try that again. Log base 2. Now 4 can be written as 2 to the second, right? And so let me try to highlight that. 2 to the second is the same as 4, right? So since 4 can be written as 2 to the second, we have this inverse idea, log base 2 and exponential base 2 leaves us with just 2. So that means log base 2 of 4 is just going to give us a 2 plus log base 2 of x. Okay, and that was number 7. Let's do number 8. Number 8 has a quotient, and so we go ahead and apply the quotient rule, which just says we can write this as 2 different logs, log base 2 of 16 minus log base 2 of y. Now, just like the last problem, we can actually take a look at this and simplify that. We can write this as log base 2, and just like the last one, 16 can be written as 2 to the fourth power, right? 2 times 2 times 2 times 2 times 2 is 16. And that really shows us that we have an inverse situation. And so that is just going to simplify down to 4. So log base 2 of 16 is just 4. And we have 4 minus log base 2 of y. And we're done. Okay, those are the rules. And what's next? Write each expression as a sum or difference of logarithms. Express the exponents as factors. Yeah, same directions. So, so we want to write this as ln, but like I said, if you're not used to that notation, I don't think it's a bad idea to write it as log base e. And then remember, this is a product, so now we've got log base e of e to the fifth plus log base e of y. And the only reason why we do that is because then it really shows quickly that, oh yeah, natural log and base e are inverses. And it's just going to leave us with 5 plus, and let's now write it, our final answer, as ln instead of log base e, even though they're the same thing. It's just sort of standard practice. It has its own special name. It's a special log. So this is what, number 9. It should be 5 plus the natural log of y. Now let's take a look at the next one. And it says, same directions, express exponents as factors. Okay, so I'm seeing multiplication again. So we're going to write this as log base 2 of 16 plus log base 2 of the square root of y. Now, as you remember before, log base 2 of 16 can be written as 2 raised to the fourth power. And you may think nothing can be simplified here, but remember that logarithms and exponents are inverses of each other, so really you should write this square root. Remember the square root? Index of 2, power of 1 can be written as a exponent, right? So this is going to be log base 2 of y raised to the 1/2 power. Okay, well, let's finish this thing off. I got a log base 2 and an exponential base 2. So down, simplifies down to a 4. Remember the rule that says this exponent can be written, exponent of a log can be written as a factor or product. So now it's 1/2 times log base 2 of y. Okay, so that's our final there. Final is, once again, it's going to be 4 plus 1/2 log base 2 of y. Okay, what's going on here now? Okay, a little more complicated, but once again, it's product. So we know that this is going to be log base 3 of z to the 6th plus log base 3 of the square root. Now remember, once again, that square root should be written as an exponent. So let's just do that right now. So this is going to be now quantity z to the 6th plus 2 raised to the 1/2 power. And now we just apply that exponential logarithmic rule that says if you have an exponent, that can be written out in front, and we've got this exponent that can be written out in front as a product. So that's going to be 6 times log base 3 of z plus 1/2 times log. You don't have to put a times right there, right? Just like when you have a number in front of an x. 1/2 times log base 3 of z to the 6th plus 2. And there you go. Okay, what's next? Okay, the quotient rule. So using the quotient rule, now when you don't have any base here, that means it's a base 10, okay? So we've got log base 10, and we don't have to write the 10 there, but this is log base, or just log of x to the 4th minus, because it's a quotient rule, log of the cube root of x minus 4. Now, once again, we probably should write, we notice that we have an exponent, so that'll simplify out in front. Right, so this is going to be 4 times log of x minus log of, and let's rewrite this x minus 4, the cube root, as raised to the 1/3 power. Once again, how do we get that? Remember from way back when, right? Here's the numerator, the index is the denominator. And because it is an exponent, it can be written out in front as a product. We've got an answer for log of x minus 1/3 log of x minus 4. Write the expression. Now we're going the opposite direction. We're trying to write it as a single log. We're compressing it together. Using the same properties, by the way. Now, as long as the bases are the same, you can rewrite this sum of two logs as a product of the arguments. Okay, so this is going to be now log of 20 times 5. Well, we know log of 20 times 5 is 100. Can that be simplified any further? And the answer is yes, because wait, what's the base? You don't have to put it in, but it might be helpful to remember that's a base 10. And this log base 10, now the argument, we'll do this in red, can be written as an exponent, right? 10 to the second power. 10 to the second power is 100. Now you've got log base 10 and exponential base 10. This leaves us with the answer of 2. Okay, next problem. Write it as a single log. So they're both base 2, so then we have no problems. We can write it as log base 2. This is addition, so you write it as a product of x times 6. Let's write it as 6x, just since we usually put the coefficient in front. X times 6, or just 6x. And I don't believe that can be simplified any further, so that is it. Write the expression as a single log. Base 3, subtraction. Okay, log base 3 of the quotient rule. So that's going to be 135 divided by 5. Now, 135 divided by 5 is 27. And wait a minute. 27 is just 3 to the third power. And when I see log base 3 and exponential base 3, I know that simplifies to just that exponent, which is 3. It's a lot of 3's there. All right, number 16. Okay, now we have a crazy exponent, right? But we do know exponents and logs are inverses, so we're kind of hopeful here. So what we're going to do is we're going to take this exponent and use the quotient rule. This is now 10, and it's going to be log of 24 divided by 3. 10 to the, and maybe it's helpful, the common log, what's the base? 10. Oh, great. Now what's 24 divided by 3? That's just going to be 8. And so a lot of nice things are going to happen for us now. A base of 10 and a log base 10 undo because they're inverses, and we're left with just 8. So you see these properties are kind of nice in some ways. Write the expression as a single log. Write the expression as a single log. Almost looks like a single log, but it's being multiplied. Being multiplied by 2, and remember we can kind of we can do that rule in reverse, which gives us log base 4 of k to the second power. Okay, number 18, write the expression single log. No problem, and once again this is doable because the bases are both 5. At different bases, you could not use the product rule. So let's do it. It's going to be log base 5, and then it's going to be the product, right? It's going to be x times x plus 7, rather. Okay, so we wrote it as a single log. And, you know, I meant to put, darn it, I did forget to do that. I meant to put these in my math lab just to see if they had an issue. I really think leaving it like this is just fine. Write the expression as a single log. Well, this is written as a single log. If they don't like that, you may want to distribute that x and write it as x squared plus 7x, but I would be okay with just leaving it. I meant to check that. So those are two the same thing. I'd be fine with it like that. Anyhow, if my lab doesn't like that, then try that, okay? Just by multiplying it out. I don't think that's going to be an issue. Once again, I almost always put it in my math lab, and I just forgot to put it in. I don't want to stop my video now. So anyways, write the expression as a single log. Okay, the natural log is log base e, so we know the bases are the same. Before we actually apply the product rule, we are going to really want to rewrite these as exponents. So now we've got the natural log of x to the 7th plus the natural log of z to the 5th. Now we can write it as a single log. That's going to be, wow, that's going to be the natural log of x to the 7th times z to the 5th. That's writing it as a single log. Next problem. Yikes, what's this stuff here? Okay, so look at that. We've got 1/2 out in front being multiplied, so that could be written as an exponent. We've got this 4 being multiplied, so that could be written as an exponent. Okay, let's do that first. So this is going to be log base 4 of x to the 1/2 plus log base 4 of quantity x minus 7 to the 4th power. Now we're going to use the product rule, that we can write this as a single logarithm as a product. Log base 4 of x to the 1/2 power times x minus 7 to the 4th power. And there you go. Okay, next problem. Write the expression as a single log. Okay, so this is a subtraction problem. So I'm going to use the quotient rule. The quotient rule just says if the bases are the same, and they're both 7 base, I could write this as a quotient of x squared minus 100 over x plus 10. Now, this looks kind of complicated, but you know, something nice is going to happen here. Log base 7. Now, it turns out, if you remember, that the numerator is a difference of two squares, right? X squared minus 10 squared, or 100. So that factors down to x plus 10 times x minus 10. And down below, we already had a factor of x plus 10. So you know that common factors will reduce. And now we're left with log base 7 of x minus 10. Okay, use the, oh yeah, see, they didn't have change of base, but use the change of base formula. Hey, look at that. Okay, it's formula. Different books probably called it a little differently. But anyways, use the change of base formula and a calculator to evaluate the logarithm, okay? So I look at that, it says log base 2. I look at my calculator, no log base 2. I do have a common log or a natural log, so it's your choice. I'm going to pick the natural log. I could go either way. Natural log of 20 divided by the natural log of 2. And when I put that in the calculator, and this says round it, okay, I must have erased that part, so I'm not sure what it wants to round to, but I'm getting 4.3219, 32192805. I'm sure they don't want that many decimals. Usually they say round it. Let's see, what's the next one? Does it say round? Oh, there we go. Round to 4 decimal places. So let's just do that here. That's going to be 4.3219. So right, 1, 2, 3, 4. Look at the number to the right's less than 5. Okay, so this is approximately And that is what this guy is approximately equal to. Once again, and this is our last problem, I believe. All right. Find the logarithm using the change of base formula. So find the logarithm. This is going to be approximation round to 4 decimal places, okay? Once again, you can either use the common log base 10 of 3, over log base 10 of 38, or you could also use, which is going to be equivalent, or natural log of 3 over the natural log of 38. And that gives you the same exact answer, and I put that in the calculator, and I get approximately 0.3020. All right, I hope that helped, and I hope you guys are having a great day. Take care. Bye.